Actually, I wanted to get things started with a, wow, I'm very loud now, with a top hat question that I had sort of planned to do last time, which was these, imagine you're trapped in a canoe in the middle of this peaceful lake with no paddles, and you want to get back to the shore. And then you notice that there's a big pile of rocks in the canoe. Is it possible, using your amazing physics knowledge, to kind of propel yourself back to the shore? So think about this. Check with your neighbor. Service is C. 82% of you voted for that, and also, so yes, but also you should throw the rocks away from the shore. That's the idea with conservation of momentum that I was looking for exactly. So, C I like. And let's do an example of just sort of what that looks like. Oh, there's too much to wish for. There wouldn't be a glitch. Yeah, I'm not seeing the, oh, you know what? It's my fault. I didn't plug in the USB. Let's try this. There we go. So, let's do an example. Laura, whose mass is 35 kilograms, so let's actually start writing down my knowns and unknowns, since that's worth a couple of points, isn't it? Is stranded without a paddle in a 65 kilogram canoe. So let's call the canoe C. Kilograms. 5 meters from the shore. She has 10 kilograms of rocks on board the canoe. So let's make those rocks 10 kilograms. Those are all going to be kind of important. We can try to draw a canoe, and then there's a person inside there, which we'll call Laura. There's the canoe, and then she's got sitting beside her. I'll just draw a circle and label it rocks. This is like the initial situation, and that tends to be chapter 6 and chapter 7 problems. You tend to draw the sketch twice, once for initial and once for final. We're right now in chapter 6, by the way, which is about momentum. Chapter 7, which is next week, will be about energy. But it's sort of similar chapters. Chapter 6 problems, you have initial and final momentum, and you have conservation of momentum. Chapter 7, you have initial and final energy, and conservation of energy. So it's just sort of a different way of solving physics problems. That's a little bit more general and sort of a useful technique. So, okay. So what we're going to do is define the system to be all three things. Is Laura, the rocks, and the canoe. And V initial equals 0 for all of these. So I can take a red dashed line and kind of draw it around all of these. Not the water, I guess, but just the canoe and all of its occupants. And then the final situation, she throws the rocks. So if the rocks are going this way, then I think what's going to happen is Laura plus the canoe, we'll just draw a little stick figure there, of Laura and canoe, they're going this way. But you still have this system defined as being all of them. So whatever the initial momentum of the system was, the final momentum of the system must be the same thing. And so we can define plus x is to the right. We know that V rock final x is negative 10 meters per second, because x is to the right. And we know that V of Laura and the canoe, final x is equal to question mark, that's what we're trying to find. And the mass of Laura plus the canoe, so that's LC I guess, is equal to 35 plus 65 is 100 kilograms. So the assumption here is that there's no external forces, external, I guess, unbalanced forces. So I guess there would be two external forces, which would be gravity acting downwards and the normal force from the lake, I guess, acting upwards. But there's no external unbalanced forces on the system. And I would say that drag of the water on the canoe is negligible. I don't know if it really is negligible, but we're going to assume that. Because otherwise I can't solve the problem. So I would say that the initial plus impulse, this is the impulse momentum theorem, is the final. So the initial momentum is 0. The impulse is 0. So the final has to equal 0. So I don't know how to do bar charts or something like that, but if you have plus x momentum, you kind of draw the 0. I don't know if I can put this on as green. Oops, sorry. Green. Initial and the is 0. The final is 0. Or the impulse is 0. So what you're going to equal here is two kind of, you're going to have a negative, momentum from the rocks and a positive momentum from the canoe and Laura. And the rocks, and then this is P of the rocks, P of the Laura and the canoe will be positive, and those will bounce each other out. So there's a big effort in the textbook to try to draw momentum bar charts, and that's sort of what they look like. They're not always so useful. Okay, so and then the represent mathematically is you just take that bar chart and you write it out. So the mass of the rocks times v of the rock initial in the x plus the mass of Laura in the canoe times v Laura in the canoe initial x is equal, or plus, I guess, plus j. J being the impulse, equals the mass of the rocks v final in the x direction plus the mass of Laura in the canoe v Laura in the canoe final x. And so this is 0 plus 0 plus 0 is equal to, again, mass of the rocks times v of the rocks final x plus mass of Laura in the canoe, v Laura in the canoe final x. So you get that v Laura in the canoe final is equal to negative mr divided by m Laura in the canoe times v rocks final in the x direction. So it's going to be negative 10 divided by 100 times negative 10. You get v Laura canoe final in the x direction is plus 1 meter per second. And this, by the way, is this is toward the shore if the rocks are thrown away from the shore. Okay? You guys feel okay about that? Sort of a simple little example showing how to use conservation momentum. Please come on in. Okay. A couple of announcements. Term test 1 has been marked. There's like the little histogram just showing what the marks looked like. There were 901 students that wrote the test. Average was, and the median were both 69%, so half the class got less, half the class got more. 69. I didn't curve the grades at all. There's a kind of a little bump here I noticed. There's almost like a histogram, but then there's this A+ sort of bump. I don't know. I mean, I've actually had students literally come up to me and say, oh, I already have transfer credits for physics 151 and 152, and I'm in this course. And I said, well, why are you in this course? That's ridiculous. And he said to me, I'm here to boost my GPA. And I was like, oh, okay, well, that's good. That's nice. You know, so I can't do anything about students like that. It's fine. But I would just say to you that you know, the purpose of university is to learn, and in order to learn, you have to challenge yourself. And taking easy courses to boost your GPA is not a very good way to do that. I also think that, you know, in the future, if it's not already happening, I think med schools and grad schools are going to look carefully for evidence of people doing this. And I think that someone with a lower GPA than you who challenged themselves into courses that they should be in is going to get boosted ahead of you in admissions. If there's any evidence of it, I think you should be careful, because I think it'll come back and bite you. But there you go. That's sort of what it looks like. Hopefully you can see it. There was an email that got sent out to you from a system called gradescope.ca. Hopefully you're able to find that, and if not, it's maybe in your spam folder or something, but you have to, there's a special link in there, and if you click on that link in that email, you will see a scan of your test. I think there's one for the multiple choice side and one for the written answer side, but when you see the written answer side, you should be able to see what you got out of 8. It's the same exact rubric that you used for yourself for self-marking the mock quiz. 2 points for the sketch and translate, 2 points for the free body diagram, 2 points for setting up all the equations, and then 2 points for actually solving it. And so every time you kind of are doing correct steps towards the answer, you get this partial credit, which adds up to 8. So it was one person who went through all 900, I guess, of these and marked them. So it's possible and probable, I guess, that he may have made some mistakes. So take a look. And if you do see a mistake and you'd like me to correct it, I will do that. Just click on, I think on Gradescope, you can click on remark request. I hope that goes smoothly. If not, let me know. But then do that by October 27th. I'll go in there and I'll fix any mistakes I see. Okay. Questions about that? General questions about that, or how are we doing? How balcony people doing? I look like a balcony, front row, middle. Okay. Yep. Ready? Good catch.
Is it possible that the Scantron didn't scan one of my answers, because it showed that I didn't answer anything for one of the questions, but I'm pretty sure I circled something on the bubble sheet. Is it possible that the Scantron just didn't register my answer?
Yeah, so the regrade request can also go for the Scantron. If you think there's a mistake, any kind of mistake in the marking, let me know. Either by clicking on the remark, or by clicking on, or just sending me an email. We have all the scans. We've kept them in a box, so we can dig it up if you really want to look at it. But if you think there's some problem with the scanning, I can fix that as well. I want to make sure that you get marked properly. Okay. Some birthdays. Phoebe, one of the Phoebes, there's 2. Lexi, Mathule, Aiden, Uncle Tetsu says, happy birthday. I like those cakes. Okay, some really great questions on the pre-course survey. One was a baseball and a cricket ball having different masses and maybe different velocities collide midair and move off in different directions. Would it be possible for one of the balls to experience a larger change in momentum than the other during the collision? And the idea here is no, because in a midair collision like this, there is an external force actually, and that's gravity, but we tend to neglect gravity, which seems like it might be a strange thing to do. So I guess there would be more gravity force on the more massive ball, but during the collision itself, just before the collision to just after the collision, the delta T there is very, very small, because collisions happen over a small amount of time. So small forces like gravity have a small impulse during the collision, or an explosion, I guess. So there's no net external, impulse, so momentum is conserved. And so whatever momentum change one ball picks up, it has to be equal and opposite to the momentum change that the other ball picks up. Same magnitude. Okay? clarify the significance of impulse versus momentum, I would say that momentum is a property of an object. So if it's not moving, the momentum is 0. If it's moving, mass times velocity is its momentum. Impulse is the change in momentum. And that happens to have an equation which is that it's equal to the force multiplied times the time. There's actually, I guess, a little area under a curve kind of thing for variable force. Yeah, there seems to be a hissing or something, right? Thank you. Okay. And then, surprisingly, these turn out to have the exact same units, which is good. Since the impulse is the change in momentum, meaning that's the final momentum minus the initial momentum, you're going to subtract two things. The difference has to have the same units as either thing. And I think I worked this out last time, but a Newton is a kilogram meters per second squared. Multiply that times seconds. It cancels one of the seconds on the bottom. You get kilograms meters per second. So it's not a coincidence, but it's kind of nice. And it kind of came up, an impulse is the graph, the area under the graph of force versus time. We're going to talk a little bit more about that. But usually what we do is we assume it's a constant force or something, and we figure out what the average force is in the middle. And then it's a rectangle, force times time. There's time, delta t or something, and then there's average force. So we say that J is equal to average force times delta t. Something like that. Okay, and then there was a whole question about the gelatin. And the idea here is that the impulse is the same in both situations because it says, in a lab environment, you're investigating the impulse of a force on a brick when the brick's speed is reduced from 2.5 meters per second to a complete stop. And it's done in two different ways. Either it hits a piece of wood or it hits a piece of gelatin. So the question here is what is fixed? There's three things. There's the change in momentum, there's the force, and there's the time of the collision. So which of those three things is fixed in this situation? It's the change in momentum. Because the initial was the mass of the brick times 2.5, and the final is 0. So delta P is fixed in this case. So this was the question from the survey. As the change in momentum is equal to impulse, why the longer object interacts with object 2, the greater the impulse. That is true if the force is the fixed thing. If F is the same, then longer time means longer impulse. However, when the same object stops in different times after collisions, why is the change in momentum the same? That's because, in that case, it's the delta P that's fixed by the problem. So I think in the case of the gelatin and the wood, the force would be greater with the wood and the time would be less. And with the gelatin, the force is less and the time is greater, but the impulse is the same in both cases because that's the fixed thing. Sometimes with these equations, you have to, when you're comparing things, you have to think, what is the thing that's fixed? Okay. So some really great discussions there in the pre-class survey. Appreciate that. Okay. So conservation of momentum, we mentioned that it's not always a thing. Certainly in free fall, momentum is not conserved because there's an external force of gravity, which is pretty important. Momentum is up, later the momentum is down. It's constantly changing. So when is momentum conserved? Well, internal molecular forces within a baseball come in pairs and they cancel each other out and have no effect on the momentum of the ball itself. Also, I would say that if you're inside a car and you're pushing against the dashboard, that's not going to have an effect on the momentum of the whole car because it's an internal force. That's why you can't make your car go by pushing on the dashboard, because you need an external force. So when the external forces either are balanced, so they add up to 0, or when you can kind of neglect them for some reason, then you have conservation of momentum. So when does it happen? Collisions and explosions. So for most collisions, the forces involved in the collision are much greater than any external forces. Like friction or gravity or something. And so therefore, the sum of the momentums of all the objects just before the collision equals the sum of the momenta of all the objects just after the collision. It kind of looks like that, I guess, before and after. So there are some examples of collisions. The other one that comes up a lot in this is explosions. So a firecracker exploding, for example, the total momentum of all the pieces just after the explosion equals the total momentum of the firecracker just before it exploded. And it's got vectors in it. Remember, momentum is a vector, so I guess the impulse is also a vector. So let's do a top hat question on that. So this is going to be 2 questions in a row about the same situation of a basketball. So what it's going to do is it's going to bounce. And, oh, lucky, I almost hit your tripod there, but it bounced right over it. In the bounce itself, there's a collision with the floor. And so that is going to change the momentum just before and after the collision. So I'm thinking about that change, and I want to split it up, thank you, into the y component and the x component. So this question is about the x component, and the next question will be about the y component. Because this whole conservation of momentum has 2 equations, one for the x, one for the y. You do it twice. So please think about this. Think pair share. So think about it, find a neighbor, check your neighbor, and then vote together. Yeah, that's the one that I liked. We'll do really quickly. Here. So basically, P initial in the x direction is equal to the mass of 0.1 times the plus 5 meters per second. So it's equal, I guess, to plus 0.5 kilograms times meters per second. Sorry, the units are a little. And then P final x is going to be, for the same reason, plus 0.5. It doesn't speed up or slow down. That's a little surprising. But then delta P in the x direction is P final x minus P initial x. So it's 0 plus 0.5 minus 0.5 equals 0. So the next question is about the y direction. Please, if you think you know it, please tell your neighbor. Discuss. What? 87% of you voted for D, which was the one that I liked as well. And the way I got that is I said, again, same sort of thing. P initial in the y direction is the mass times negative 5, because it's going down. So it starts off with negative 0.5 kilograms meters per second. And then P final in the y direction is equal to 0.1 times plus 4. It bounces, but it must have lost some kind of energy or something in the bounce, because it comes up with less speed than it went down with. But anyway, plus 0.4 kilograms meters per second. So delta P in the y direction is P final minus P initial. So it's plus 0.4 minus negative 0.5, and you get plus 0.9 kilograms meters per second. So, and this was what I was talking about before, which is that often a force is kind of variable. And I guess in any collision, the force is extremely variable. It goes up, then it goes down. So it's 0, 0, 0, goes up, and then it goes down. But in physics, we say that there's some sort of area under a graph, also known as the integral or something. But the area of this rectangle, if this is T final, and this is T initial, is going to be the average force times T final minus T initial. And that's going to be true for the x component of the force and the y component of the force. So J, this impulse, has units of newtons per second, and the impulse momentum theorem states, there's two equations actually. The x component of the impulse changes the x component of the momentum, and the y component of the impulse changes the y component of the momentum. So this next top hat, I'm not sure how well it's going to show up on your screen. Oh, there's the other equation. Delta px equals jx, and delta py equals jy. So let's look at these two graphs. This is a bit of a tricky question. It's actually problem set 5, question 15. Not this week's problem set, but next week's problem set, actually. So you got time to think about this. But this is a plot of the x component of a force versus time. So what happens is that there's a hockey puck, which is sliding along with 0 force in the x direction. Then, all of a sudden, it receives a positive x impulse at time t1. And then it goes away. So it's going to change the x component of the momentum at time t1. Then, later on, there's another, I think what's happening is somebody has a hockey stick and they're hitting the puck. Almost like when you had that mallet, you were hitting the bowling ball with the mallet. I don't know if you've done that this week yet. You're giving a quick impulse, and you can change the direction of the impulse to be in the plus x direction or the plus y direction. So then, at time t equals 2 seconds, you give an impulse in the plus y direction. So then are shown A, B, C, and D are trajectories of the puck's motion in the xy plane as viewed from above. So 3 of these trajectories are possible, and 1 of them is impossible. Which of the trajectories shown below, wait a second, could be the result of these forces? Sorry, I think that's wrong, right? Okay. I actually think this is messed up. I think it should have been which is the not. So let's close this one. I'm going to have to not use the top hat for this one because I think I screwed it up. So I apologize about that. But let's actually look at this because so another way of looking at this question is that there's 3 correct answers. So what I would do is look at this trajectory. So what I think is happening for A is that initially it's moving at time 0 in the negative x direction. And then it stops and sits here from 1 to 2. So that would be possible if there was a plus x impulse that stopped it. And then at time 2, it starts going up to point 3. So I would say that A is, yes, possible. It just depends on what the initial velocity is. So I think that's the difference between these different trajectories is they have different initial velocities, I guess. So it's possible something was coming along, got hit in the plus x direction, stopped, then got hit again at time 2 in the plus y direction, went up. So what about B? So it's already going with some negative y velocity. Then it turns left and goes on a diagonal because it must have received an impulse in the plus x direction. So that's good. Then it turns left again because the y component has gone to 0. So that's also possible, I think. So I like this one as well. Yes, possible. I better check the problem set on this too. And then problem C, so it's starting at rest, 0, 1 second, or here. Then it receives an x component of its velocity, so that's okay. Then at 2, this is a bit weird. It goes straight up. So yes, it's received a y component of its velocity, but it's also must have a negative x component, and it doesn't here. So this is not possible. You can't get rid of the x component of the velocity unless you have a negative x impulse on it at time 2. Makes sense? What about D? So D, it starts off with this negative x and negative y momentum. At time 1, the x goes away because it must have received a positive x impulse, so that's good. Then at time 2, t is 2 seconds, it must have received an upward impulse to stop it. So I like that as well. Yes, possible. So I'll make sure that the problem, question 15 on problem set 5 is correct, because the top hat that I did today was a bit screwed up. But do you get it? These little impulses, these hits, what they do is they change that component of the momentum. Okay. Moving right along. A 0.15 kilogram baseball flies to the left with an initial velocity of negative 30 meters per second. So P initial x is equal to the mass times V initial x. It's going to be 0.15 kilograms times negative 30. So P initial x is equal to negative 4.5 kilograms meters per second. Vladimir Guerrero Jr. hits it and provides an average force of plus 12,000 newtons for 1 millisecond. So first question, I guess, would be, what is the impulse delivered to the ball? Well, I would say that Jx is equal to this force times delta t. So it's going to be 12,000 newtons times, I guess, 10 to the power minus 3 seconds. I ended up with, I guess you're just going to move the decimal 3 to the left. You're going to get plus 12 newtons times seconds. So that's the impulse delivered by the bat. And then second question is, what's the final velocity? Well, you can find the final momentum is going to be the initial momentum plus the impulse. So you're going to get negative 4.5 plus 12. So the final momentum is plus 7.5 kilograms meters per second. And then you can just use our definition for momentum. Remember that P final x is equal to the mass times V final x. So you can solve that out for V final x is that momentum divided by the mass. So it's the 7.5. Don't forget to divide by 0.15 kilograms, and you get the V final is plus 50 meters per second, which we hope is a home run. Okay. Seem okay? I want to talk a little bit about, so we've talked a little bit about when you fix the change in momentum, or sorry, when you, I guess, have a certain force in a certain time, you get a certain impulse. I want to go back to the idea of when you fix the change in momentum, you can change the force or change the time to get the same change in momentum. So this is this following through thing. So in order to really change momentum, you want to apply the greatest force for as long as possible. So I think that this comes up in sports when they say to follow through. A golfer swings all the way through to try to increase the time of impact with the ball rather than trying to stop yourself short. Same thing with swinging a baseball. And this is this is a funny thing with from Toy Story was, I think Buzz Lightyear was trying to convince Woody that he can fly, and he ended up, he said, no, you can't fly, and then he jumped and bounced off a bunch of things, and Woody said, that's not flying, that's falling with style. So bungee jumping is where you fall with style. Okay, so there's a bungee which extends. So I guess there's two ways of stopping after you fall off a bridge. You could either hit the rocks below, and there could be a large force over a short amount of time, or you could have a bungee which stretches as you're falling. That increases the delta T, and so decreases the force on you. And so it doesn't hurt as much. It doesn't kill you. Extend the time during which the momentum is reduced. So that's a case where the delta P is fixed. You have to stop, basically. You have some initial speed. You have to stop. But you can change delta T or change the force. Crashing with stuff. So when a car is out of control, it's better to crash into a stack of hay than it is to crash into a concrete wall. Physics reason here is that it's the same impulse either way, assuming that you have the same car and the same initial speed, and the same final speed, which is 0, but it's either, they did it with, I guess, the font size here, a little force over a long time versus a large force over a short time. You could kind of plow through the hay for a little while. It explains, airbags as well. You can either hit the dashboard or you can hit a bag of air and slow you down. So you're increasing the time of collision in order to decrease the force. There's something about like riding with a punch, getting punched with style. So if someone hits you and you really try to stay perfectly still and hold your ground, that's going to shorten the duration of the impact and it's going to hurt more. But if you let yourself kind of ride with the punch and get pushed backwards, you'll increase the duration of the punch and it'll be a less force. And then you can do the opposite. If you're trying to karate chop something, if you really kind of quickly hit somehow and decrease the delta T, you can deliver a greater force for the same stopping motion of your hand, I guess. So that's, if you're an expert, you can hit something with a very, very small delta T and increase that force. So we have a demo that I do want to set up. Let's see. I'm just going to delete that top hat question that we did last time because it wasn't good. But this one will be okay. And we can show it here. So what I've got, and maybe what we should do is switch to aux video and show you the setup. It's broad. So you have a chance to predict this. We have two balls, the rubber ball and the clay ball, both of which I can hang from the thing. So the difference there being that one is bouncy, and if it hits a solid object like this block of wood, for example, then it bounces. The other one is clay, so if it hits the wood or anything, it kind of deforms a little bit and it doesn't bounce. And they're the same mass, by the way, which we've got a pan balance here, nicely to show that. Got the same mass, so that's good. And we also have the same string, so we're going to tie it to the string. I'm going to put it in the little clamp thing here. Whoop. I've got to do it carefully. And I'm going to release it. Maybe I'll start with the rubber ball and then see if the rubber ball tips over I have a piece of tape here, see if it knocks over the block. Then I'll try the clay ball and see if it knocks over the block. And I think it's set up so that one's going to do it and the other one's going to not do it, or they'll both do it. But you make a prediction, and then we'll try it.
It should be set up just to unscrew it.
Okay, I'll just unscrew and
I
then.
think the top,
Okay.
the clay is a lot smaller, obviously, so you have to screw it a little
Okay.
bit more. The tape should mean everything should be set up okay.
And of course, we're thinking here about the impulse. There's an impulse delivered by the ball to the piece of wood, right? A is you think it's not going to matter, the same mass. B is you vote for putty, the clay ball, and C is you vote for the bouncy ball. Once, twice, then we'll try it. And I press aux plate. Okay. Let's see what people vote. Ooh, people are voting for the bouncy ball. Let's see. Ready? I'm going to unscrew the... Oh. Let's try that one again, shall we? I put it at the wrong place, sorry. I put it at the wrong starting place. Let's try again. Okay, that one definitely knocked it over. Now let's try the clay ball. So it goes here. Good. I moved it. Now let's do the same. So same exact height, same mass. Okay, it doesn't knock it. So that's the idea. Thank you very much. Thank you for the applause. Always nice when these things work out. But the basic idea is that, so why the rubber ball? So this also came up, of course, in the pre-class quiz. So a lump of putty, rubber ball have equal mass. Both are thrown with equal speed against the wall because it's swung down, I guess, the same amount of distance or something like that. Difference is that one stops and the other reverses its velocity. Okay? So the idea here is that for the putty, I guess, you've got delta P is equal to P final minus P initial, which approximately equals 0 minus P initial. So it's approximately equal to, I guess, these magnitudes, if you do absolute magnitudes or something like that, is going to be P initial. But if you do the rubber ball, then delta P is going to be P final minus P initial. It's going to be something like negative P initial minus P initial, negative 2 P initial. So the delta P here, delta P magnitude is approximately equal to 2 times P initial. So it's twice as much because it's a vector. If you reverse direction, you're actually giving it twice the bump as if you have just stopping it. So this is why bouncing impulses are generally greater when objects bounce. So example, if you were to catch a falling flower with your hands, you would provide some impulse to reduce its momentum. But if you were then to throw it upwards again, you'd be doing twice as much impulse, right? And that's kind of what a bouncing thing is like. The floor is not only stopping it, it's also reversing it. And you can actually use this in these, if you look at these, it's called a Pelton wheel, that takes the energy of falling water from a waterfall and converts it into rotational motion. The Pelton wheel is designed to actually splash the water back upwards again, and it gets twice the amount of momentum and, from the water that way, twice the impulse. And you can sort of see it here. Here you've got some initial velocity, you've got a negative force, and it changes the momentum during this time. So positive momentum changes to negative momentum. Okay. So please finish off reading chapter 6. Let me know on the pre-course survey for Friday if there's anything in particular you want me to take up, and I'll see you Friday.